today we are going to do section 3.3 on page 285. What we're going to do is we're going to handle integration involving square roots of the sum or difference of squares, such as the one you see on top, such as square root of a squared minus x squared, a squared plus x squared, and x squared minus a squared. Now notice the two kinds where the x squared goes in front or in the back of that subtraction, it does make a difference, because if it's in at the end of the a squared minus x squared, that means x squared cannot be bigger than a squared, okay? Because you're taking the square root. You'll be taking the square root of a negative number, which is not defined. So then as a result, we are going to, but the integration we're going to do is not just those things themselves, but even stuff that involves it up to a point. So it gives us quite a bit of options as to how to handle this. The logic behind it is something like this. That is, if you have the square root of a squared and minus x squared, for example, we have, let's see, we start with something that has a squared minus x squared, and what we're going to do is let x equal to sine theta, okay, in this case. No, actually, to be exact, we'll let x equal to 8. We need to take care of the a. So a sine theta. The point of that is so that by the time you do a squared minus x squared, that becomes a squared sine squared theta, and that would become, that becomes 1 minus sine squared, which is cosine squared, right? So then we get this a squared minus times cosine squared, and that is even better because then we take the square root, and that just equaled a cosine theta. And then, well, in taking the square root, we have to worry about the sign. There's a plus or minus square root. But in this case, we define the sine squared, the theta, to be between pi over 2 to negative pi over 2 in such that the cosine is going to be positive the whole time, and therefore we don't have to worry about the negative version of it. In general, I should mention now that when you integrate something that has an absolute value, such as if you need to take the integral of, say, x, of absolute value of x, how would you do that? The way you do it is your answer end up having two options. That is, in the area where x is positive, then it's the same as just x itself, okay? Because there's no difference, okay? Now let me draw the absolute value of x, the graph here. The absolute value of x looks like that. So if you're integrating this part, then that's no difference, just y equal to x, okay, that line. So, but if you're integrating this part, then that's actually equal to you have to slap a minus sign in front. If you're integrating this part, because that's the same, because the graph there is identical y equal to minus x. So when you integrate the absolute value, it is you have to sometimes watch out for in case what happens when x is negative. Now, having said that, in this particular section, we are going to more or less ignore that fact and just focus on x being positive. I mean, there are times that you will have to slap on a negative sign for the whole thing to make sense. Otherwise, your problem's weird. But for this section, being that we're learning the trigonometric substitution, we will, for the most part, not pay too much attention to this detail, okay? But bear this in mind. And after I say this, I'm just not going to say too much about it, because we're going to focus on how to integrate, okay, with trigonometric substitutions instead of get bogged down by details. But do remember that when you integrate the absolute value, and if it's negative, if it ends up being in the negative area, you do need to slap on the negative sign normally. But anyway, so let's move on. Okay, in this case, we're doing, because we defined this angle between minus pi over 2 to pi over 2, which and the cosine is going to end up the cosine will end up being positive, so we don't have to worry about it. Lucky us, right? And so let's move on. In fact, the fact that the angle, where the angle is defined, is not even going to come up, because we're just going to, set up the proper ground rules to mean that this is going to be positive. The next thing I want to talk about is if you have an angle such that theta is there's a theta involved, and especially there's a sine theta involved, the way to get the angle back is to draw that angle. Here's your theta. For what is sine theta? Sine theta would be something like, you have x will be here and a would be here, whereas sine theta would be x over a, okay, as this equation shows. Sine theta is x over a, so therefore how in the drawing form, that's x and that would be your a. And what is that? That would be by the Pythagoras theorem, a squared minus x squared square root. Then what is that is good in case you ever need to figure out what cosine a is, or tangent, which I don't think we need to care about that. But the point is, but that's there if you need to know what that side is, and also or cosine or tangent. The general idea is that and then theta itself, of course, is the inverse sine. Okay, if you have to, so theta is sine inverse of x over a, in case you need that. But that's just a quick review of basic trigonometric facts. So let's move along and look at the next page. We have a bunch of strategies. How to integrate things that's a squared minus x squared. Now the strategy says, number one, when you see something that has a squared minus x squared in it, first see if you know how to integrate it by the ways method, a quick way of how you might be able to do this already, such as the integral of the first one, 1 over square root of a squared minus x squared. Now how would you do that? Now, for example, the square root of a 1 over a squared minus x squared is equal to sine inverse, okay, as you can see there on top. And there's only 1 here, but the 1 can be changed to a with a small amount of algebra. And yeah, anyway, the standard formula, of course, has a in it. This is just something I copy and pasted from Calculus 1. But as you can see, that one can be done without doing any substitutions. So the square root of 1 over a squared minus x squared is simply some kind of sine inverse with some a involved in there for adjustment. And the next one, when you have x on top and then the square root thing on the bottom, that you can the x dx on top takes care of du. See, then you can just do a substitution of u equal to a squared minus x squared. And that's the same with the last one too. If you have to integrate x times square root of a squared minus x squared, again you let u equal that the x dx there takes care of the u substitution. As a result, all you have to do is just let u equal to x squared a squared minus x squared. So those things we have already done in the past. You may or may not remember it, but you sort of have a feel for it. However, so what we're going to do, the method we are learning today, the strategy, is for things that those previous methods don't work. Okay, so this because the x is in the wrong, the extra x, if you have any, is in the wrong spot or something like that. So then we are going to do this substitution trick. Mainly, the most important point is we're going to let x equal to a sine theta, and then in this case, the square root thing will turn into a cosine theta, as you can see, which is much easier to do than some square root and subtraction and all that stuff, right? And then everything will come out nicely. Now, to see an example of it, let's evaluate Let's look at example 3.21, where we are supposed to evaluate square root of something, 9 minus x squared. So then, let me see. Example 3.21. All right, we have 9 minus x squared. So what we're going to do is follow that line where we let x equal to 3 sine theta. Once you plug that in, the algebra that follows is fairly straightforward because everything works out nicely, and very soon you will end up at where you get the integral of 9 cosine squared theta. Now, cosine squared theta is not that obvious how to integrate, but if you look up the previous section, then you remember that to integrate something like cosine squared, it has a second squared power, which is annoying. So what you're going to do is use the half angle formula and knock it down to the cosine 2 theta form. The half angle formula for cosine squared is 1/2 plus 1/2 cosine 2 theta. And so once you get that, then you are pretty set, because now you have cosine to only 1 power, even though it has a 2 inside, but that can be taken care of. So then you integrate that, you end up with just theta. And then, let's see, they have sine theta, cosine theta. What? No. There is no need to turn the sine 2 theta into 2 sine theta, cosine theta. I see no benefit in that. And that is just, yeah. Actually, fine. You do have to figure out what cosine sine 2 theta is, because you have to plug x back into it. And the fastest way is to convert sine 2 theta by the trig identity, which equals to 2 sine theta cosine theta. So at that point, I suppose you can plug that back, and then you have to figure out what cosine theta is. You already know what sine theta is. Sine theta is this thing. Yeah, sine theta is x over a. So where a in this case is 3. So then you have to figure out so cosine theta, if you draw this triangle out, is the adjacent over hypotenuse is a squared minus x squared square root over a, where in this case a is 3. So once you do that, then the whole thing does come out. Whereas theta itself, is just the sine inverse of x over 3. And that will be your final answer after you clean up some of the algebra here. The process is quite tedious with a lot of writing, so I'm going to skip most of it, and but otherwise it's quite straightforward. So please do this example as your homework. Example 3.21. Next, let's look at example 3.22, where we have the integrate of something minus x squared, a squared minus x squared, except that there's a complication here. There's an extra x on the bottom, which so far, without this new trick that we learned, we don't know how to integrate something like that. I mean, that's just, yeah, what do you do with the x? Okay, so then we are going to use the new trick we learned, which is let x equal to a sine theta right here. See, in our case a equal to 2, so x equal to 2 sine theta, and that means dx equal to 2 cosine theta d theta. And then we might even want to construct that triangle. Now, we'll do the triangle a little later in case we need it. We probably need it though. Anyway, but let's do the math first, okay? And plug everything in here. We get the integral of 4 minus x squared. That is equal to 4 minus 4, 2 times 4 sine squared theta. And then divided by, what's x? Well, x is 2 sine theta. We already said that. Write that down. And then we have dx. Okay, dx is this stuff, so we'll write that down. Dx is 2 cosine theta d theta. All right, so that will be equal to take 2. That's yeah. There's a 2 here, which we will take out, And then it becomes 1 minus sine squared, which is cosine. And take the square root, becomes cosine. So the whole thing is 2 cosine theta divided by 2 sine theta times another cosine theta, 2 cosine theta. All right, and then next we have now actually, being that we have 2 cosine thetas here, it becomes a squared situation. So we're gonna turn that back to sine theta so everything's consistent and see where that leads us. And there, that gives us, bring us to that will be 2 times the cosine theta, cosine squared theta. There's 2 of them, two of 2's. So cosine squared theta becomes 1 minus sine squared. And then we have the 2 sine theta on the bottom. And then d theta. At this point, we have one situation is 1 over sine theta on this side, and the other situation is just sine theta. So we have the cosecant, integral of cosecant, and then the integral of sine. So at this point, we are going to look up what the integral of cosecant is, which we did in the previous section. There's a set formula for it, and we're just going to quote that formula. Okay, and then of course the integral of sine is some kind of negative cosine. And at that, so we are going to once we look up those charts, then we are going to plug theta back in. See, right, as shown in your book. The cosecant is 1 over sine, which is the sine is here, so the cosecant is easy to do. It's just 2 over x. Okay, 1 over sine is 2 over x. But what about the other thing, the cotangent? Well, to figure out the cotangent of theta, we're gonna draw that triangle that I was talking about earlier. Here's our triangle, which is actually the same triangle, I think. But we're gonna draw it again each time we do this. So here's our theta, and x over 2 is sine theta. Okay, so x over 2 is equal to sine theta right here, which means this side is 4 minus x squared. Now with that definition down, then we can figure out what the cotangent is. The cotangent is inverse tangent. Tangent is opposite divided by hypotenuse. Divided by adjacent. So cotangent is adjacent over hypotenuse. So that's how you plug in, how you get the square root of 4 minus x squared over x for the cotangent part. The cosecant is just 1 over sine. We already mentioned that. And that's 2 over x. So you got that. And then the cosine is square root of 4 over 2. And that's how you get the answer, as you can see here. So that's the end of example 3.23. For your homework, please do example 3.22 as well. Even though I've gone over some of it, there are certain details that it would do well to be able to pull it off yourself without looking at it. So next, let's look at example 3.23. So example 3.23, we have the integral of x cubed times the square root of something. And that actually, the way it works out, being that you can take one of the x out and save it as x ds for the u-substitution, and then you will have a perfectly normal x squared. You have x squared here and x squared here left. What happens then is you can do a u-substitution with u equals to this whole thing inside 1 minus x squared. And then what's the x squared left here will become something like 1 minus u or something, and then the whole thing will come out very nicely. And that's the first way that your book does. So please do that. Do it as your homework. But we will proceed to the second method, which is instead of using the u-substitution that we already know, we're going to use the new trick that we recently learned, the trigonometric substitution. Now in that case, then we will, as before, let x equal to sine theta, being that a is 1 in this case, and then we are going to have, of course, dx equal to cosine theta d theta. And at that point, we have plug everything in here. We get x cubed which is sine third power theta. And the square root of this thing is 1 minus sine squared is cosine squared. Take the square root, it's just cosine. Okay, so this cosine. And then the dx is another cosine theta d theta. So we have cosine squared situation here. So we have a sine cubed, cosine squared. And as you might remember, this is a situation we learned in the previous section where the power of sine is odd. And what you're supposed to do is when one of the power is odd, then you will take one out and keep it with d theta as your u-substitution. So we're going to be doing a second u-substitution. No, it's not a second one. It's just the first one. Never mind. Anyway, we're going to do the u-substitution as we have learned before. And in this case, we are going to let u be cosine theta. The reason is because we're saving a sine theta over here with d theta for the u substitution, and to become sine theta d theta we need u to be cosine theta or something like that. So we let u equals to cosine theta. This is to repeat what we learned in the last section. And then du of course equal to minus sine. And once you get here, then everything else kind of plugs in nicely. So you plug all this stuff in, and you come up with some kind of a u polynomial, which integrates easily by the power rule. And once you do that, then you have to plug. Our u is cosine theta, so you need to plug the cosine theta back into the u. So then you get a bunch of cosine thetas here. So let's look at the book. See, first we got to the u, okay, and then we got to the cosine theta because u is cosine theta. You plug the cosine theta back, and then lastly you need to plug the cosine theta back. What was cosine theta again? Cosine theta is some kind of relationship with sine theta. So we need to plug that back too. Let's see. Give me a second here. So to do that, to figure out cosine theta, we have to draw that triangle again. Well, or you can do it in your head if you've done this enough times, finally got it memorized. So x equal to sine theta. So that means this is theta, and this is 1, and this is x. Okay, x over 1 equal to sine theta, which means cosine theta by the Pythagoras theorem is 1 minus x squared. Okay, 1 minus x squared. Actually not cosine theta, the adjacent side I mean. And then the cosine theta then becomes the square root of 1 minus x squared divided by 1, which is just the square root of 1 minus x squared, as it says. That's the cosine theta. So once we figure out what the cosine theta is in terms of x, because everything has to go back to x, okay? I mean, all our substitutions are just temporary. We have to get our answer back. So once you figure out what cosine theta is, you plug it all back into the cosine 5 and 3 and all that stuff, and you come up with this fairly complicated looking answer, which is correct. So please finish this problem in your homework, example 3.23. Next, let's look at the situation where you have a squared plus x squared under square root. How will we do that? We're going to pull some trick that's similar. What we're going to do is turn it into a perfect square in using trigonometric identity, and so that we can take the square root easily. But being that this is a plus, we're going to use the trigonometric identity that involves the plus, which is the tangent squared theta plus 1 equal to secant squared. Now to do that, then what we're going to do, let's look at the problem solving strategy at the bottom of the page, 289, where we have, we let x equal to tangent, okay, x equal to a times tangent theta. Now at that point, then we have a dx, of course, equal to the derivative of tangent is secant squared, theta d theta, and then we have, so you plug everything in here. If you plug x equal to a equal to tangent theta in here, then you have a squared tangent theta squared plus, sorry, I wrote that first. that's x squared, okay, plus a squared, I'll write it here, which is equal to, we'll take the a out because a is positive. We'll take the a out, then we have the square root of tangent squared plus 1, okay, this thing right here, which is secant squared theta. And that would be equal to, that's an 8, not a 9. Okay, and so that would be just equal to a secant theta, no squared. Now notice that this is due to our theta being defined in a convenient area. The a secant squared is the square root. Secant is always positive in this area, so we don't have to worry about the absolute value when we take out the square root, which is nice. Okay, so having said that, so what happens that in this substitution, we effectively got rid of the square root, which makes life a lot better, probably. Now, if eventually you still have to draw that triangle, I guess I'll draw it later. Okay, where if you have secant squared, what are the other angles similar to this thing? But we'll draw that in a little bit. Let's look at an example where we integrate something called 1 over 1 plus x squared. In example 3.24, we are looking at the integral of 1 over 1 plus x squared, which is what? If you remember this thing from the Calculus 1, we did this in Calculus 1. Okay, the inverse, let me show you. If you don't remember, you probably won't, because I sure didn't. Anyway, but I remember something like this. As you can see, the integral of 1 over 1 plus x is simply, is the sine h inverse. Okay, that is, see on the left side here, the sine h, the antiderivative is simply sine h inverse of x. So we already know what this is. However, we're going to use this thing as a practice to see how our trigonometric substitution works, and also to assume that you've forgotten about that since Calculus 1. So let's do that, and to do the new trick we just learned, something about letting x equal to tangent. Okay, so in this situation, we'll let x equal to a tangent theta and see what falls out. So we'll follow that rule, and that gets us x. Once you plug in x equal to tangent theta, then of course dx is the secant squared, as I mentioned earlier. And then we have to draw that thing. Let's draw it. All right. In this case, first, write down x equal to tangent theta. A is 1 in this case, tangent theta. Okay, and then we have our theta here. What is tangent theta? The tangent theta means x is this side over this side is tangent theta. So which means theta equals to, let's see, I can't see that. Give me a second. Well, I don't know what I was looking for. Tangent theta equals x over 1. Okay, so this is x, this is 1. Anyway, so x equal to tangent theta, and then the hypotenuse, we have to figure this out, is Pythagoras theorem again, is 1 squared plus x squared square root, which happens to be that thing, which is nice. So that's good. So we got our triangle, and the next thing we're gonna do is dx over the square. We'll plug everything in. When you plug everything in, we get dx. So 1 plus x squared, 1 plus tangent squared, and then square root is secant theta. And then, of course, we need to figure out what write down dx is secant squared, as I have already written over there, d theta. But we'll write that down too. So secant squared theta, d theta. Sorry, this should be d theta. Secant squared theta, d theta. All right, that's good. and then that is simply the integral of secant, okay? And the integral of secant, as we learned in the previous chapter, is already, the answer is already given. And we should keep that in a cheat sheet somewhere and pull it out. And we pull it out to be the answer as shown here. But once we get that answer, which is natural log of secant theta tangent theta, we still have to figure out what it is, okay, in terms of x. So if secant theta, what is secant theta? Secant theta is 1 over cosine, so it's this square root divided by 1. It's the opposite of the reversed option of cosine. So that's secant theta, and then tangent theta, of course, is just x, and that gets your answer. So even though this problem is pretty short, I still would like you to do them, redo them as homework so that you'll have a good, strong grasp of it. Now, in fact, at the end, on the next page, your book even have you take the derivative of that big long answer. What is the answer again? It's not that long, but it's fairly long, right? And the book actually takes the derivative of that answer to prove that it really does become the integrand of this thing. Now, so I would like you to take the derivative as well to just, I don't know, practice doing the derivatives. It actually comes out very nicely. So please do that also. Yeah. Anyway, so that's that. And let's look at the next example. The next example is exactly the same problem. And what do they want? They want you to use the hyperbolic substitution. Yeah, let's not. Because for one thing, like I already showed you, the integral of this thing actually is the hyperbolic function of sine minus x, as we have learned previously in the, Okay, as we have learned previously, okay? As you can see here, the integral of 1 minus x squared, 1 over, is simply, 1 plus x squared, what am I talking about? Okay, 1 plus. Is simply sine h inverse. Now, and here's the question, of course, is that doesn't look anything like what we just came up with, okay? We just came up with natural log of something. And then your book went ahead and showed you the sine h inverse is actually the same as what we came up with. There's a reason for that. It's because the hyperbolic functions are made up stuff. They are not actual real things in the sense that they're just some combination of e to the power x and then e to the power minus x, and then you mess around with it. That's why it's just, in other words, it's just another name of saying the same thing. That's why they come out to be the same. So let's not work too hard on that and move on. Now, we're not gonna, in my course, your book likes to yank out the hyperbolic function once in a while for no reason. We are learning here the trigonometric substitution, not the hyperbolic. They look like trigonometric, but they are not. Okay, there's very little use for them, if any. So far, I haven't really figured out what they're good for. Except they are cute because they have very similar properties as the trigonometric functions. But still, the trigonometric function is what we're going after, so we're going to ignore the hyperbolic stuff and focus on how to use trigonometric substitutions, which is the purpose of our being here. So the next example is the book wants you to find the arc length. I don't know why we should do that. So that's, I guess you can go ahead and do that as an example, maybe. Or maybe not. Yeah, okay. Go ahead and do example 3.26 as an exam as your homework. Now, if you don't remember the formula for the arc length, just look it up. It's in the previous, it's taught in Calculus 1, which actually got repeated in chapter 3 here. So yeah, just look it up. It's very simple. It's square root of 1 plus f prime squared. And then you go ahead and apply the tangent, the rule we just learned. Let u equal to tangent theta, a tangent theta, and then the whole thing will fall out. However, there is one thing I should mention, that your result end up being the integral of secant cubed. Now, remember how that's done? Well, that was done, let's see, which problem was it? 19 or something? Well, whatever it was, we did that earlier. In fact, we did it something like 3 times. So please look that up, and then you know where the book found this answer. Okay, it was a big, long integration. So yeah. So that's good enough. Next, the last thing we want to talk about is the integral of x squared minus a squared. The x squared minus a squared is different in the sense that with the other things we did so far, we have a fairly limited domain. You know, like for example, like this thing, where x has to be x cannot be bigger than 1, okay? Because if it is, then you got a problem. But this case where we where x is going in front, then x has to be bigger. It cannot be smaller than 1. If it's smaller than 1, you're gonna have and you're gonna be taking the integral of a negative number, so which is not acceptable. So then we have, in this case, therefore, when we consider x squared minus a squared, we have to look for, let's see what we're doing. This time we're going to substitute as x equal to a secant theta. Secant theta, okay? And then the derivative of then the derivative of the secant is secant tangent. So dx then equal to secant tangent d theta, dx, a secant tangent, secant theta tangent theta, and then d theta. All right, so you're going to plug all that in. As you can see, this trick is going to be slightly harder than before because your dx is going to have more stuff in it. So it might be slightly harder. But there's also another concern, is that when you plug this thing into the square root, then you will of course end up with a squared tangent square theta. And when you take the square root, then you have that situation here where the square root has to be just a tangent theta for one situation when is for x is less than negative a, which means makes it positive, okay? And then the other situation is that, let's see, I didn't include all of it. Let's see, sorry. Let's see the whole thing. Okay, for x bigger than a, then everything's positive and we're all happy. But when x is less than negative a, you have to watch out that the a tangent theta, you have to slap a negative sign on it, as we have mentioned earlier. However, the book doesn't seem to be that much of a stickler for that. Sometimes they mention that in the answers of homework, sometimes they don't. And so we will, for the most part, sort of ignore that for now. Okay, because we're focusing on learning the skill, and we'll remember to slap on the negative sign in in the future. So then once we figure that out, then the whole thing works the same way. We have to find this works almost identically to the other situation where you plug it in and then something comes out. And to do that, to see that, please do example 3.27 as your homework. Specifically, I should mention that this is on page 294. The triangles you draw in this case, well, this is for when things are positive. Okay, everything's fine. If secant is x minus a, then that's your triangle, and all the other triangles fall out nicely from the Pythagoras theorem. But if x is negative, if you have a negative value, then things might get a bit annoying in the sense that you might have to remember the negative signs. But as I say, the book seems to often not pay attention to the negative case. Okay, just focus on the positive, which is I guess we'll do that if we'll follow the book's lead. So if the book does that, so will we. Other than that, everything's the same. The question is whether we should slap on a negative sign or not. So and that marks the end of this section. We will please do homework for this part. Oh, I forgot to mention one thing. There's a slight error on page 293. Where is 293? There's a slight error where it says, in the problem solving strategies, is where it says secant squared plus 1 is tangent squared, right here. And this part in the strategies, Okay, where it says secant theta plus 1, it shouldn't read plus 1, it should be minus, okay? Because based on this formula, see, secant squared minus 1 is tangent squared. Just a slight typo, no big deal. Okay, so homework, please do, let's see, exam problems 139, 143. Problem 143, please do it in both the old u-substitution and the new trigonometric substitution that we just learned. 145, same thing. 147, 49, 51, 61, 63. 163, I have written down the answer in the back is wrong. We'll talk about that later, okay, if that's the case. So please do those homework, and then in the next video, I will talk about them.